So this is the last lecture, and the task of this lecture is to do the phase space analysis. So in the first lecture, we did the paraproduct estimate with everything norms. And in the second lecture, we did the selection of the trees. And now that we have the trees, we should prove a paraproduct estimate for the trees. So just to extract the module that we haven't dealt with. So we define these trees, and maybe I draw one more picture to remind you. So we had the singularity of the multiplier, and then it shows always the top frequency. And from the top frequency, we draw a cone with opening much larger than 90 degrees. And then we choose all the Whitney cubes that are inside this cone. And those are the family of frequency boxes that are chosen by that tree. And for each of these, we of course put an adaptive multiple. And if we were just working with no localization in space and just summing over those frequency boxes, we could use the Koifman-Meyer estimate to bound this paraproduct. But now, as it were in the tree selection, to conclude the proof, we should deal with the tree paraproduct, which meant that we take these frequency boxes corresponding to the tree, and then looking at the spatial side, we take the intervals corresponding to those frequency boxes. And not only that, also the right-hand side of the estimate has to be changed. So there we have to get the bound by size of that tree. And designing this size was somehow the core difficulty in making this tree selection to work. So the size has to be large enough so that we can prove this estimate today. But it also had to be small enough to conclude one of the computations of the estimate. Okay, so now to start proving this estimate, let's speak some more notation. So we started with this sum over tiles. So we have a Fourier multiplier adapted to a tile, the frequency box, and then we localize in space into spatial support of the frequency box in question. And then we sum over family of tiles. And now the target is to deal with family F, who are the chosen trees, the chosen tiles in a tree. So this is this form here, lambda pt. And now we split the tree in two parts. So we take first the boundary tiles, and the boundary tiles were the ones which are touching the region between the dashed line and the dotted line. So frequency boxes here give rise to the boundary. So just restricting attention to those is the first form. And then the second form is when we restrict the attention to the tiles whose frequency boxes are here inside the cone dashboard. Okay. And then reminder about the sizes. And I went a bit fast through this last time. So now I try to repeat a bit. So what were these things? So we had two sizes for the boundary and one size for the core. So let's first look at the core size. So here we have a family of multipliers whose Fourier transforms are basically adapted to certain box. And this box is defined here. So we take a big square around the top frequency. And now, of course, these sizes are defined for index n, one index n at a time. So we better project this picture to something. So if we project it, say down. So we are having a line of the psi variable, or in our use psi for both the top frequency and the variable. But now suppose the top frequency is here. Then we take roughly radius 2 to minus j. I think I put there something more. There is plus 10. So this is the box where the Fourier support of this guy is. So we do the Fourier projection at the way worst possible to this box around the top frequency, and then we restrict in space in a smooth way to some of the intervals in the tree. So we restrict first in Fourier side, then in space side. And then we just take supremum over all the scales. So somehow the point here, we don't talk about frequency boxes as seen by the tree, but we just talk about scales and locations. And then in the Fourier, we just remember the size. So we are not seeing somehow these individuals. We are just seeing their somehow, we are just seeing big intervals who would contain them, contain their projections. Okay, and this is somehow, this is very rough size. And it is, it was dealt in the tree selection as it was dealt. Another remaining property was this calibration that we must have bound by eligibility norm for this one. And here we see that this is actually just a triviality, because now you see if you put the absolute value, sorry, the measure inside the integral, and you see that this is roughly behaving as a characteristic function. So you can pull the L infinity norm of pi star f out. And now you have L infinity norm of pi star f, and because this is normalized convolution, L1 normalized convolution kernel, that is of course bounded by L infinity norm of f. And this was the upper bound for size that we had to have. And in that sense, the core size is small. And then the other two sizes are the ones that see really the tiles. The boundary size, it was just looking the tiles whose frequency boxes are here in the boundary region. And then it restricts in frequency to vicinity of one of them. And then it restricts in space, and then you take supremum over all the tiles. Not scales and location, but now really tiles. Okay, and this is something we could also deal with in the tree selection. So excluding that sense, and also the bound by L infinity norm, it follows exactly by the same argument as here. So we have average first in space, we pull out the L infinity norm, then we are left with the convolution, and it's again a normalized kernel, roughly. So we get bound by L infinity norm. Okay, and then the third size is this sum. Now we again take frequency and time for projection as here above, but instead of taking L infinity over the family ET, we take little L2 sum over these things, and we normalize by the measure of the support of the tree. And now this thing, we will see in the next slide that it appears very easily, but the somehow trickier part is of course to bound at the L infinity. But let's see first how these two first sizes appear in the bound, and then let's see why they are. So we bound first the boundary part of the tree, and this is absolutely easy. So first, in the first line, we have written here just the definition, and then we just do Hölder's inequality in the integral. So one of the functions we pull out as an L infinity norm, and the other two we take it as L2 norms, and then we are left with the sum. This L infinity guy we pull further as a supremum out of the sum, and for the other two we do Hölder's inequality in the sum. Okay, and now once we have done this, we see that the quantities that appear are exactly the sizes we saw. And this is somehow no surprise in view of how the proof of the Goldman-Mayer multiplier theorem works. So also there was the case 1, where all the multipliers had value 0 at 0, where we could do just Cauchy parts. So this is basically the same. And when you look at this picture, this is also the same picture as there, because we are confined in this strip. So when we project anything from this strip, namely the region where the boundary frequency boxes live, when we project to any of the directions, they are avoiding the top frequency. So now we have somehow this kind of mean zero property in both directions. And okay, we could, of course, write this kind of square function for any family of times, but we will need this special property of having the projections far from top frequency in all or both variables. We need that property in order to have a good bound for this sum size. So to prove the sum size by an infinity norm, this is where we need the restriction to the boundary. Okay, and now let's look very briefly how that goes. So we have our tree, and we have the family of types. And now without loss of generality, we can assume that for each j, which is now the scale parameter, there exists at most one frequency box of that cycle. Okay. This can always be arranged by repeating the pigeonhole. Okay, And now under this assumption, if we fix the file, and then we look at this term appearing in the sum, we can write it in two parts. So we have the kernel, which maybe I keep the occupation, not to cause confusion. Okay, so now we would have here the function fn, but we can split the function fn in two parts. So there is the part one, who is the support of the tree dilated a bit. And then there is the other part, who is the part of the function who is far away from it. Now these two terms, let's call them x of t and y. And now we should somehow deal the sums over these things separately. So it's okay to use more blackboards or better what? Okay, I will use it. Okay, so let's start looking at the XP because this is the interesting one. So we have the sum over the tiles in the family, and then we have the sum over the XPs and their L2 norms or this. And this thing we can of course split into two sums. We sum over the scales, and then for each scale we have the dyadic intervals corresponding to the tiles of that frequency box. But the dyadic intervals of the same side length are pairwise disjoint. So I can put the sum over dyadic intervals inside the L2 norm square, because this is just integral of the quantity squared. And now these dyadic intervals are contained in the top interval. So more precisely, I can put here the top interval, and then I remain with n j, with now the multiplier corresponding to the frequency box of this scale. And then there is the function on which it is in that. Okay, but now, as it is, if this is my top frequency box, the remaining frequency boxes are just larger and larger. So I can find the function whose Fourier transform is supported in a ball of roughly this diameter, and who is larger than 1 inside this set whose diameter is inverse of this. So let's denote such a function by theta and replace this by theta. Okay. And now, because these are coming from different scales, and I'm again having one factor whose Fourier transform is supported, say, here. And then when I have a product, the Fourier transform of the product is the convolution of the Fourier transforms, and the support is the Minkowski sum of this thing, and then the bound function around origin, whose side length is much smaller. So I will dilate this thing just a bit when I have the multiplication. And now we can divide this by modulo some number to see that we have, say, 100 sums, and in each of the sums, the Fourier transforms of these terms are disjointly supported, and the multiplier is bounded. So we can use the L2 orthogonality now because of the Fourier disjointness. So we can put the sum inside. And now this is a projection where we have bounded C. So this guy is an L2 bounded operator. So we get this thing, and now dividing and multiplying by the measure of the top interval, we get the bound by the measure of the top interval times L. And that's why we can bound the sum size, this first part of the sum size, by the L. And it was important that we have this lacunar structure here, and this lacunar structure was guaranteed by the fact that all the ties that are relevant here are coming from the boundary. If we had this kind of core ties here around, this thing wouldn't work. Okay, and then there is the remaining part, YP, where we are restricting the Fn far away from the support of the tree. This argument I completely skip, but here the idea is that you just take some decay of this kernel, because now I'm having the 3 times IT here, and I should be looking at the function restricted somewhere here. So the intervals that are relevant are well inside this thing, and I'm looking points here. So I can pull some decay from this guy, and this decay is enough to sum up. So that's how this easier part looks. And that's where the A infinity bound comes from. Okay. And now, having seen that even this sum can be bounded by the L infinity norm, we know that the treatment of the boundary part of the tree is really done. So for the boundary part of the tree, we have really all the estimates. So the only thing that remains is to prove similar thing for the core. So the boundary part is now there. Then the core part was the part where we can actually forget the tree. So here we just have this picture that we have some family of intervals, and we have some Fourier projections, and we have the uncertainty principal relation. But beyond that, we just have the tree form and we control these quantities that have nothing to do or very little to do. And of course, the problem at the core is now, as in the difficult case, of course, when layer multiplier, the projections cause piling up. And we will use the other size, which is not providing any cancellation like before. And now to do this part, we will use the method of phase space projections and the LP estimate. So the idea is that the LP estimate for product products, which knows how to deal with this piling up phenomenon, but at the level of LP norms, that estimate doesn't remember the phase space localization. So in order to remember the phase space localization, we have to try to replace F by something that stays inside the region direction. And this turned out to be somewhat complicated. But to motivate first, why should one even try to believe that something like that can be done? Let's look at how it happens in the discrete Walsh model. So Walsh model is doing Fourier analysis in the unit interval with a different group. And the good thing with the Walsh model is that here the uncertainty principle works in a different way. So the function can have compact support both in space and time. So now the physical space is the interval 0, 1, and this other interval 0, infinity is parameterized into frequencies. And then for a dyadic rectangle in this set, if the area is 1, we call it a type, and if the area is 2, we call it phi type. And then we define the preliminary set of Walsh functions. I should draw some pictures. Okay, so the point is, we start here, and then for number j, we fix the division to pieces of side length into j. This is for sure not the dyadic number, but let's not worry. And then for each interval, we define the Walsh function corresponding to this kind of box. These are the boxes in the subscript. We define the Walsh function corresponding to that box to be the characteristic function in the projection down, which is renormalized in L2. Okay, so now we have a function for every tile who is touching the x-axis. And then we define this kind of additional operation to produce functions for other tiles. And using this mechanism, we can produce functions for all tiles. So we take a white tile who is 2 neighboring tiles, and then we cut it either vertically or horizontally. So when we cut it vertically, we say that these tiles are just, the resulting tile is just summing the neighboring tiles up. So if we start it here, we would get the characteristic function of this larger bit. And now it's a larger set, so the larger set, so somehow the Fourier transform should be considered as having different support, and that's why we come. And similarly, if we want to move up, this is the first thing, we should modulate. So in a way, we should be multiplying by cosine something. And this means that we produce some cancellation. And this is this is coming from just subtracting these things one. And there are some special cases you can see that the hard functions appear somewhere here. But in general, if you just take a random square, the Walsh function will be somewhat strange. It's kind of irregular structure, but it has many good properties. And it serves as a model of all set properties. Okay. Then some folklore. So if we have two tiles and the boxes in the picture are disjoint, then we have L2 orthogonal, which is going to happen for either the spatial supports being disjoint, or then them having the frequency supports disjoint so that there is cancellation to make the inner products. Okay, then we denote the span of set of Walsh functions by the span of the tiles, just to simplify the notation. And then there is a fact that if we have families who cover exactly the same region, then the corresponding function spaces, the subspaces of L2, are equal. And then forward. For these tiles, we will use the same notation as for our Fourier tiles. So when we have a tile, the IP is the space interval, omega p is the frequency interval. And then when we have tiles or bitiles, we can define the partial order for them by looking at inclusion. So when we have tiles that are meeting, we can say that these are and this order is used instead of this discussion about subordination and things like that we have previously. And now for these Walsh functions, as it were, we have an honest subspace of L2 when we restrict the phase plane support something. This is something that didn't happen in the Fourier world because there are always planes and you cannot talk about subspaces that easily. But now we have actually subspace, and for a subspace, we will have an orthogonal projection. So if we take a family of tiles, and we assume that this tile, this family of tiles, a union of bitiles, so convex means basically thing like that, so that in terms of the order, you haven't omitted anything. And if these are bitiles, it's now an exercise that you can find a family of tiles that covers this thing. For instance, if this long one is bitile, this thing is a tile. It will be one member in the tile. And once you have this kind of cover, if you let Px be the minimal tile that contains a point, we can define the orthogonal projection by just taking for each point the minimal tile, and this is the same as taking this kind of sum. Okay, so now we have orthogonal projection. It's very simple to write down, and this really gives you restriction both in space and limits. And now suppose you are studying trees in this setting. I will skip basically everything. I just say that if we have a convex family of bitiles, which is the notion corresponding to the tree, and then we have some kind of paraproduct defined here, which would be something who is having its space plane support in that family, then using these projections, we can really say that the paraproduct, the tree paraproduct, is the tree paraproduct acting on the phase space projections, and further, it's the same as a global paraproduct acting on the phase space projections. And now, if you do the LP bound, you will get LP norms of these projections. And Now these projections, they even turn out to play well with the sizes that are relevant in the Walsh world. So things work very well. But now in the Fourier world, we don't have these pi-s. So there exists no family of operators with this thing, so that they would play well with the size and LP. Another somehow interesting task is to construct a substitute, which we will still be calling phase-space projections, although strictly speaking, it's not projection. Okay, then we should call it the para-projection. So let's make a list of wishes. What should this thing be doing? As it were, we are going to control this red thing. So the form restricted to the ties at the core of the tree acting on a triple of functions. And if we take any other triple of functions with this kind of relation to those, which is really nothing, just by pure algebra, we can write this difference as these three terms. And now, of course, in order to bound the red term, it is enough to bound the four black terms. Let's start with the first one, who is the tree para-product acting on the supposed phase plane projections. So first of all, we should complete the spatial side so that we have a global para-product acting on this tree. So in other words, we should have a form which is spatially leading outside of the tree. In the Walsh picture, this would be somehow a form that that's taking ties like this one and this one, everything that's not in the tree. So we should be able to say that a form like that, with these projections, is going to give us something small or something tractable. In the Walsh setting, of course, this would be zero, because we have the projection to some set, and then we take something that's supported outside that will give us zero. So okay, this is the first thing. We have the frequency boxes, but we are restricting outside the spatial support. We act on the phase plane projections in this manner. We should get something tractable. This is the first one. Then, when we have subtracted this CT full space, which is now the frequencies but in the full space, the second thing we need is a para-product with LP norms acting on this full space so that we will get the product of LP norms of the phase plane projections. This we have by the Koopman method. And then the final item is that we must be able to bound these phase plane projections by the size that is relevant for our group. Okay, so once we have those, we are done with the first black. Then for the other ones, and okay, maybe I should still say, the second bullet here, this is the only thing that appears in the Walsh. The first thing would be trivial in using. The remaining three things would also be zero in the Walsh setting, because when we go to the tree, we take the projection, it should keep the function pretty much the same inside the para-product. So these would be all zeros. But now we are not hoping for that, but we should claim something strong. So we are hoping that if we just extract the times projections from the para-product, and if we have a phase plane projection or no phase plane projection, we will bound the L infinity LP of those things by the size. And then, because this remaining thing, little L2 sum of the LP norm of this difference. In the Walsh setting, it's 0. So now in the Fourier setting, we are asking a lot, namely the little L1 summability, which is very, very true, but in this case, we will get the out. Okay. Now, of course, this tractable, good enough, these are somewhat approximate words. So we need to state them rigorously. So here is the theorem, which is just copied from the paper. Okay, so this is in T dimensions, and this is in the setting of unit compounds. So let's forget the T, and let's forget the N. For any T, we have a constant, so that we have the intervals that come from the tree, which is now normalized to be in the unit interval. And we have some nice input function, so we can construct the projection so that given the size we are working with, the projection has exactly the correct amount for the LP norm. Then it has this L1 LP thing I mentioned. This is the first line. And then the second line is the of the tree estimate, or an important part of it. So the sums, they are of course long, but if we see the structure, here we have the difference. We project in frequency, two frequencies support corresponding to the relevant region of the size. And then we restrict in space to the relevant portion in the support. Then we have a normal feedback. Then we just sum over all the intervals and all the scales. So this is trying to be somehow saying that when I take points, it might be that at one point I'm looking at frequencies. At one point, I'm looking at frequencies here, and then at the next point, I'm looking something more, and then again something else. And now, given a point, you must somehow find the smallest frequency frame, which contains the frequencies that are active and not. And this is what the base plane projection does. And then these estimates, they are the thing. And maybe one remark, in the first item, this is indeed the Fourier projection who is using all the region around the top frequency. But in the second item, we are actually taking projection who is far away from this center. And the reason why we think we can do that is that the same thing happens as what happened in the proof of Koitman-Meyer theorem, that even if we take a ball that is not lacunar with respect to both, so it's not somehow going towards diagonal, but it has projections that meet top frequency. Even if that happens, we always know that for one of the coordinates, we have this lapinarity property. And that will be always the coordinate on which we will be applying the second recipe. Okay, then idea of the proof. This is very nice thing, so I hope we have time to do it with something. So first, let's take the function who is Fourier supported in a ball or in an interval. This is the power. Then we do the dilations to have things that are fully supported in the ball, so radius to J. And then we have and then we have the sides who are the ones who have the anchors. Then let's take the intervals as we had in the theorem, the ones that are the three, and that have side length 2 to k, and then ek is their union. So it's union. Kxi is the number so that this sentence holds. So it's somehow the minimal scale relevant for the point. Because when we draw one more, not so precise pictures. If I now identify my intervals with other horizon boxes, as it's not. So suppose all these things are, all the upper halves correspond to their projection in the tree. If I take point, say here, the smallest interval in the tree that corresponds to that one is this. But if I go here, the smallest one will be this one. And if I'm here, the smallest one will be the huge tree. So this is what the K is. And now, like in the walls construction, we can try to just mimic. So we write f, and for any point, we take the Fourier projection to the relevant Fourier state. Okay. This is not so tractable object because the dependency on x is very strange. So using these sets ek, we can telescope this thing and we get this expression. Okay, and this is the thing that worked in the wall setting, but here we have the obvious problem that in the second term, these summands do not have the definite Fourier support because psi k is supported in the annulus, but this characteristic function has jumped this continuity, which means that the Fourier transform is completely dislocalized. So this has no good Fourier support. So we have to correct it. The first problem in the correction is that because we are working with dyadic intervals, it might happen that all these problems pile up. So this is the first thing we want to clean away from the table. So in order to do that, we take all these intervals that appear in our tree. And okay, I have written it here differently, but you can think of dilating those by factor 3. So you add the shift left and right for everyone. And we fatten all these EKs by that manner. And then when we replace in the previous sum the EKs by EK1s, we see that these problem regions, they are shifting apart. So you can see that if I have this horrible picture, that all the boundaries are here, but when I dilate by 3, the first boundary goes here, the second one here, the second one here, the third one here, so they are not aligned anymore. So that's the reason for introducing the EK ones. Okay, and then we have to really do something for them. So we will add something in these regions, and these additions they are now, because of this trick of dilating, spatially disjoint from each other. And okay, the remark with this kappa that I didn't comment is that, of course, we can right away also smooth this. We don't really know yet how much it helps, but for sure it won't hurt. And then we must recover the smoothness, which is easy to do, and the vanishing moments, which is also easy to do if you know what to do. So let's start with the moments. So we take the Fourier transform and we apply an anti-differentiation. On the Fourier side, it is very easy. We just divide by the Fourier symbol. We define this thing, and then we take this smoothened EK1, and there we put this antiderivative. Then this whole thing we differentiate twice so that these derivatives die, and we replace the summands by this thing. And what now really happened is that if you are inside the EK, say nothing, then you recover exactly the expression that we had in the non-smooth case. Then there is the region in the middle where you really don't have so much going on, and then in the end you have added some bound. And now with this modification, we will have the Schwarz decay because we are smooth, and we will have the vanishing moments in the sense that we have good decay towards change. So this is the decay. And then how you bound it? You first write the expression that appears in the theorem, and then you expand the G, and you expand the F also in the little Daily manner. And then the second sum is what you should be bounding. And because I can't do it all, I just say that the heart of the matter is to obtain summability in this scale parameter J. So J is the scale parameter from the construction of the phase plane projection. And now if J is smaller than I, so we are having smaller intervals in the what corresponds to 3 than the length of the tile to which we are projecting, we can do integration by parts. So just go to Fourier side, divide and multiply by side. This is essentially what I'm saying. And we will have this kind of decay factor. This is the choice of the order of J and I is such that this is the nice thing to get. And that's where we need the vanishing moments. And then there is the other case when J is larger than I, then this Fj minus Gj is actually supported far from the intervals of the tree. And we can use the kernel decay to get the factor which is within that case. And now putting these cases together, we can conclude the proof. And here is still somehow schematic picture on how these things look in this latter case. So if we have scale 2 to I, we are projecting to time frequency boxes whose intervals are, say, one of these red ones. And then we are looking at the phase plane projection at the scale, larger scale. We know that this Fj minus Gj is something that leaves outside of this Ej1, so it's pretty far here. And then we can use the distance between this thing where we are and this thing where the support is to get some kernel decay. Then there is the estimate, the second estimate in the theorem, where we estimate G away from the tree. And this is similar thing, but in a way it's dual. There we don't use the vanishing moments, but we use the smoothness and again integrate by parts. The arguments are of similar nature, but they are different. And then to estimate this total G, there is a Whitney type decomposition of the space, which looks roughly like this. And somehow inside each of the red boxes, we can try to telescope the things up, and that's how we get this. And I think that was all I plan to say about phase plane projection. And now somehow this is the whole paper doing the phase plane projections. And once you have done them, you apply the para product and you feed in the estimates you get from that to the tree selection. And that concludes part for the process. So thank you.
Thank you very much. Are there any questions or comments?
It's like where does the uniformity the bilinear in the transport and the gate in this
In which part?
yes.
Okay, so it appears in the tree selection, of course, because we are not having the Whitney cubes of the line, the complement of the line, but the line must be somehow tilted. And there you okay, I draw some more pictures. So now we were working in a setting like this, but to have things work similarly in a uniform setting, we will map this with the sharing transformation to another plane, and now these Whitney cubes become lengthier. And then we have to prove para product estimates, which have this anisotropy adhering, first of all. Then the tree selection algorithm is not much different. And then in this phase plane projection, of course, we do not have this Heisenberg type relation between time and frequency, but the frequency projection is using way larger boxes than what the space. And this is an effect that sometimes it helps you, and sometimes it's very dangerous. And the special point of danger is when you do this integration by parts. So there it must happen exactly that this dilation factor, the eccentricity, it comes and goes with differentiation and integration. But yeah, it is really distributed all over. But I would say the para product and the projection are the parts which see the most in the most strong way.
Any other questions? Okay, not then let's thank Olli again. I have a little announcement for the afternoon, so we plan to go to this meeting at 6 p.m.